Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth.
Hello everyone, welcome back to Physics with Beth and Beth. I'm Beth, and today we are continuing our discussion of AP Physics 1 Unit 3 on work, energy, and power with a couple quick practice problems on power. That is a tongue twister. Okay, so this is our first problem here. We have a child that's pulling a wagon with a force of 75 newtons at an angle of 30 degrees above the horizontal. If the wagon moves a total of 42 meters in 180 seconds, what is the power delivered by the child? So whenever we see a problem like this, oftentimes students get a little overwhelmed when we're talking about power because you have so many different ways you can calculate an answer. We actually have 3 different equations for calculating power. Our first one is that power is equal to, well, overall we know in general that power is equal to our work over our change in time. But we can calculate work as being equal to the parallel component of a force times the displacement divided by a change in time. We can calculate this as a change in energy over a change in time. Or we can also notice that, hey, delta x divided by delta t, displacement over time, that's equal to velocity. So this is also just equal to the parallel component of force times velocity. So those are 3 different ways we can calculate this that we can choose from, and sometimes that can be a little overwhelming. So whenever you approach a power problem like this, a good question to ask is, okay, what information do I have that would make calculating this easiest? So we know we're given a force, so that's a good indication that we're probably going to be wanting to use one of these 2. And then we're given that we're moving a total of 42 meters in 180 seconds. Hey, 42 meters in 180 seconds, that's looking like every value that we need for this little equation right there. So this is the one that we're going to be using today. So, a quick note, it's only the parallel component of force, the component of force that is parallel to our movement, that contributes to our work and therefore our power. So let's just do a quick little free body diagram. We've got a little wagon. We know that a child is pulling, we're just going to say this is the force of the pull at 30 degrees above the horizontal, so at like this, and we know we're looking for the component of the force of their pull that is parallel to our motion. We can assume that they are moving perfectly straight so that this problem actually is able to be solved. So this would be the x component of the force of our pull, which we know because we are masters at calculating different components of a vector at this point, that this is just going to be equal to the force of my pull times cosine of theta. So if I want to calculate this power, all I have to do, oh goodness, my power is just equal to the parallel component of my force, which is the force of my pull times cosine of 30. So force of pull times cosine of 30 times my change in distance, 42 meters, over my change in time, 180 seconds. Now, a quick thing to note, sometimes today all of our values were given in really pretty units that are really easy for us to work with. They were given in the SI standard units, standard international units. So we have 42 meters. We don't have anything in kilometers or centimeters or, heaven forbid, inches. Goodness gracious, imperial units. Our time is given in seconds, which is what we want. We have a force that's given in newtons. So all of our units line up, and those are exactly the things that we're going to be wanting to use today. But if they're given to you in any other units, you're going to have to convert. Make sure your masses are in kilograms. Make sure your distances are in meters. Make sure your units of time are in seconds. Because whenever we break down the units of watts, those are the components of 1 watt, the units of power. So I'll stop my jabbering and get to actually calculating this. We know that our power is equal to the force of our pull, that's 75 newtons, times cosine 30, times 42 meters, this is newtons, divided by 180 seconds. So we have newtons times meters divided by seconds, that's Newton meters per joules per second, that is 1 watt. So that is good. So this is equal to, if we calculate this, altogether, this is equal to roughly 15 watts. And there you go, that's all there is to it. Just a little bit of finding the parallel component of a force, which y'all are old hats at by now, and then knowing which equation to use, what exactly you need to plug in, and that's all we need to do. So let's move on to the second little problem here. At what minimum rate does a 60-kilogram boy use energy when, in 8 seconds, he runs up a flight of stairs that are 10 meters tall? So here, one thing I want to note real quick before we start diving into this, whenever you see a minimum rate of using energy, anything like that, a rate of using energy, that is asking about power. Those are some key words you can keep in mind. Power is a rate, something with a change in time, something that's changing over time. Okay, and then how is energy changing over time? That's power. Okay, great. Now we just have to figure out exactly which of our 3 equations we want to use in order to calculate power. Well, let's see. We're not given any kind of force here. We are given 10 meters, so maybe that could be this delta x, but calculating this force is going to be kind of gross. However, we do know how much the boy weighs, and we do know how much distance he covers. Well, we could really easily calculate the change in his potential energy from when he's at the bottom of the stairs to at the top of the stairs. So a change in energy over change in time would be much easier to calculate for us in this problem than using any of these other equations. So let's do that. So we know that power is equal to a change in energy over a change in time. We know that the change in energy, if we say he's starting at ground level, so at a height of 0, and he's going up to the top of the stairs, our change in energy is going to be our final potential energy minus our initial. I'm going to represent potential energy with a U, so our final minus our initial over our change in time. Our final energy is going to be the potential of the potential energy, or rather gravitational potential energy of this boy when he's standing at the top of the stairs. So that's going to be his mass times the acceleration of gravity times h. I'm going to say h final minus mass times the acceleration of gravity times h initial over our change in time. Well, the mass of the boy is 60 kilograms, so that's what we'll put in here and here. Our acceleration of gravity is just the same as it always is. That doesn't change here. Our final height is 10 meters, and our initial height we'll set as 0. So here we go. We can just say, I'm actually going to factor out this mg here. So we have m times g times h final minus h initial over delta t. Our mass, move back over here. Okay, our mass is 60 kilograms. The acceleration of gravity is 9.81. Our change in height, this is going to be 10 minus 0, so that's 10 meters. Oh, this is meters per second squared. Divided by our change in time. We know that the time he takes to travel up the stairs is 8 seconds. So whenever we put all of those things together, we end up calculating that this is equal to 586 joules over 8.00 seconds, which is equal to 736 watts. And that's all there is to it. The trickiest thing with power is not actually calculating it, because all of the calculations that are involved in power are things that you guys have had a lot of practice in already. The trickiest thing is identifying which equation it is that you actually want to use, so just look at the information you know and think about which of the options is going to be easiest for you on that problem. Alright, that's all we have for today. Thank you so much for sticking with me through all of that. Y'all are troopers, and happy physicsing. Oh, and a quick comment, if you guys are enjoying these videos, please let us know. There are just 2 of us sitting in a basement making these videos, and if they're helping you, we'd really like to know. They honestly, whenever anyone leaves a comment or a like or something, we're talking about it and it makes our day. So thank you so much for that. Happy physicsing.